Good afternoon, everyone. My name is Raymond. I'm the project manager for the virtual NUS project, and this is my presentation partner. This is Shu Chen. She's our GIS lead for the team. We have quite a huge team. A lot of the members are unable to make it here today, including the 3D team lead Jason. Some of our members are here on the second row. If you want, you can network with them later on. So let me first tell you about the virtual NUS project. Last year we did a presentation. For some of you all may have seen some of the materials. So this year we aim to give an update on what we did with it, what are some of the progress, and what are some of the areas that we will venture into to try to push the envelope as a research university. So virtual NUS was inspired by the bigger Virtual Singapore project, and we aim to create a high resolution, high accuracy 3D map of the entire NUS. NUS is almost 2 kilometers wide, corner to corner, and our campus consists of the Cambridge campus, the university town, and the Bukit Timah campus. What you are looking at on the screen now is a view of the virtual NUS 3D models and terrain from our virtual NUS platform. So we use a hybrid of multiple approaches, including LiDAR scanning, both handheld, tripod-based, or car-mounted, and even drone-based photogrammetry, whereby we perform computer vision to actually derive the 3D point cloud from drone photographs. So there are a lot of motivation why we want to put in so much effort to try to create a very high accuracy 3D map of the campus. So in terms of this type of models, we have a lot of typical applications, such as you can use it to do very accurate solar potential estimation. You can do very accurate 3D cadastral control. You can use it for infrastructure planning, both above the ground, above the rooftop, or underneath the ground. Okay, we can also use such accurate geometry models to do a lot of computational fluid dynamics type of simulations, such as noise propagation, such as pollutant dispersion, for example. We also use it to do utility management, indoor navigation, and a lot of the rest of the things that affect our day-to-day community of users and visitors in our campus, lifestyle around it, be it whether it's somebody staying within the campus or somebody who's new to the campus and first time visiting. I will tell you more next. So here is one example of how we use it to perform solar rooftop potential estimation based on the accurate heights and all the accurate infrastructure that was modeled within the campus itself. We can then simulate the sun going through the entire campus within a typical day, and then compute all the areas that is actually getting correct amount of sufficient amount of potential for us to actually prioritize those building rooftops for installation of solar panels. So another one, in order to perform airflow analysis for thermal comfort studies, for example, okay, we also make use of our 3D models, whereby it's quite intricate in terms of even the lift lobby, even the corridors are correctly modeled such that airflow can be correctly simulated through it instead of being blocked. All right. So next. So as a foundation of our smart campus platform, this 3D map, right, is used to actually superimpose the rest of the other 3D data layers and all the semantics on top of it. One example is this. We have set up campus-wide crowd sensing mechanism, whereby we are able to sense crowd changes per minute at every level, every building within the campus itself. So here we have a dashboard in-house to actually allow planners, security to actually look at this crowd on a per minute basis. They can also look at historical data to see if there's any anomaly. So this actually helps a lot in terms of adding visibility to utilization of facilities and spaces, because certain buildings may have a lot of meeting rooms, seminar rooms set up, but people don't frequently book it. When we book meeting rooms, usually we book the ones that we commonly use. So there are a lot of spaces that are underutilized that has gone unnoticed. So within this particular application that we built for in-house use, this is one of the things that it actually adds visibility to. So the other thing I want to talk about is the crowd flow analysis and the resource deployment part of things. Now, because virtual NUS buildings are modeled to very high accuracy, including the measurements of a particular corridor of every pillar, every wall, window, and the ceiling height due to the laser scanning. So what happens is that simulations of emergency evacuation can then be accurately simulated. The study can be done in terms of how many people can rush through a particular corridor at a particular velocity during an emergency. That is to say, with crowd sensing throughout the campus, certain buildings may have certain capacity, right? But if that threshold is crossed, okay, all meeting rooms or all seminar rooms within a building is suddenly fully filled, then at that point, if an emergency should occur, okay, people cannot actually evacuate the building fast enough. That's the kind of simulation that it can support. Next. So we get a lot of questions in terms of why are we building these buildings to such high accuracy, high fidelity, really matching every single phase of the geometry to every single point from our point cloud scan. Now, our reason is this. In order to sustain a 3D model of a campus or of the city or any city, Singapore or any other rapidly development city, maintenance is a big issue. So we are looking forward to be able to provide a platform to enable machine learning to occur. In order for machine learning, for AI, for deep learning to occur, you need ground samples. You need your ground truth as learning samples, I mean. So in this case, our photogrammetry point cloud that you see here of the Faculty of Engineering, we have painstakingly labeled it manually in terms of whether is it building or non-building, in order to allow the machine to be able to run models, okay, build their models, build their vector models and neural network to be able to detect and automatically label in the future. Next. At the building level, we also went another step ahead to try to label it in terms of the different segments of the building, be it whether is it a roof, is it a wall, is it a facility. Even for roof, if you look at the bottom left video over there, for roofs, for a typical building, okay, you may have different types of roof. First roof, the main roof, a second roof that's slightly smaller, a third roof, so on and so forth. So once we label all this, and then feed in a geometry model that's the best that a human expert can model it to, then we can enable the machine learning part to take place. So what we are doing internally for our research team under Professor Andrew Lim is that we are labeling all the 240 plus buildings of NUS, and then we are going to push it out through a platform to share this massive set of labeled point cloud to the world of researchers to see who actually can come up with better and better algorithms to actually do this automation of point cloud to model building. Because of this virtual NUS project, we end up with a very highly accurate 3D model, and that also allows us to push the envelope to try to explore other means of using it. So one, for example, is augmented reality, meant for underground utilities, assets, and services management type of usage. So because it's highly accurate, we make use of the device, mobile device gyroscope and sensors to be able to position it correctly. And then we develop a library that allows AR within a web browser. In today's augmented reality, typically you need to install an app. But our library enables you to do augmented reality within a browser to superimpose GIS data layers, be it 2D or 3D, with the real world via the device camera. So the next thing that we are looking at is that one of our team is quite good in terms of optimization. That's their research interest. So our team is quite big in terms of navigation and routing. What you are looking on the screen is the NUS Maps app. Now, NUS Maps is a three-dimensional multi-modal data set that allows room-to-room routing. We are not talking about building to building. We are talking about door to door. every single room of a particular venue that is of interest to be it the staff, the student, or the visitor of NUS. It provides turn-by-turn routing instructions in terms of even indoor walking, where to turn, and it provides a landmark instruction as well, turn after the pantry, for example. It includes multi-modal, that is to say it will advise you whether to take a particular internal shuttle bus, whether to take lift or take stairs. This is especially complicated in the case of NUS because we are on an undulating terrain. So building crossing over to building horizontally, you may end up on different levels of another building because they started on lower ground. So we have this now running, available on both the Play Store and App Store for both students, staff, and visitors to download to have a go at it. Now, the other thing that we set up was another infrastructure to allow us to receive real-time sensing of all the internal shuttle buses that is plowing up and down the entire NUS campus from Kent Ridge area in Clementi all the way to Bukit Timah. So with that, we actually get a 3D sense, okay, of the entire bus movement. Instead of telling you that the bus is going to come in 3 minutes time, 5 minutes later, the app still shows you 3 minutes. Today, consumer actually wants to know where is my bus now, right? So we provide this. This is available through the app as well, so students actually get to see all the real-time bus locations. So we wanted to do more, and in terms of navigation, we wanted to try to tackle indoors. So indoors is quite tricky in terms of, firstly, all the corridors are not being named. So you can't tell people to, go straight on road A, then turn right onto road B. All the corridors are not named. So we tried a lot of methods. So one method that we tried is to use a 360 degrees virtual tour method, whereby it should follow the motion of the mobile device to allow people to actually have a view of where they should be going, okay? But that wasn't good enough, right? This is currently functional within our campus. What you see on the screen now is the I-4.0 building, the Innovation 4.0 where our office is in. If you'd like to take a look at the live demo, you can visit us. Next. So we thought maybe we should try a 3D navigation for indoor, and that actually opens up an entirely different can of worms. We have problems with trying to define a precise position of every single device, and if we want to do augmented reality or mixed reality so that you can have a floating arrow at the intersection to tell people where to go, we first need an accurate indoor model. So we went ahead to try to create the Innovation 4.0 building interior model. The entire 3D team took a few weeks to create it to the highest level of details possible. What's different here is that this is firstly a photorealism type of 3D, so that the context provided to the user versus the environment is going to be the same. The next part is that it's real world scale, okay? So the distance of the indoor are all going to be correct. Accurately geolocated, okay, which means that brings us to our last problem, to be able to position a user indoor precisely. And we actually have a approach to use every single sensor in the device, including the accelerometer, to do something similar to simultaneous localization and mapping, the SLAM method, to try to position the user as he or she walks and keep correcting it based on all the signals, ranging from Wi-Fi signal, Bluetooth signal, even geomagnetism signal that interacts with the metal structures in the walls and the ceilings and the roof of the entire building. So with that, we enabled this through an API so that it's mobile friendly, and it supports query and filter for us to build the following app. So we are glad to announce that now inside the Innovation 4.0 building, we are able to actually do indoor localization with routing with a 2D plus 3D interior view of exactly where you can go. This was also presented to Minister Heng Swee Keat 2 weeks ago. We did a live demo in front of him when he came for the opening of the building. So in this particular solution that we have, the user actually looks at the 2D map. Okay, and when he or she holds it up, when he or she is not sure which intersection to turn at, you see the 3D against the real world context, and it actually synchronizes as you swing your device around. With this as a basis, we can then start to use this to overlay information such as arrows, text info that a seminar now is running, who's in that meeting room, which meeting is it. This particular demonstration is available currently for i4.0, and we are currently scheduling a plan to roll it out to the entire Faculty of Engineering within the next 1 month. Right, now, so with all this functionality, we had another issue inside among our users. That is to say, for the navigation, we have one single app. To check the bus timing, it used to be a separate app. To check the lesson plans and download lesson materials is another app. So staff and students of NUS actually used to need to download many apps, and they need to try to remember information, right? That, oh, my class is in room 123, I remember that, and then I switch over to NUS Maps to try to find a navigation route to room 123. After that, okay, the navigation instructions say take the A1 internal shuttle bus. So what time is A1 coming? I need to switch to another app to try to look at the timing. Oh, it says 5 minutes. So what happens is that we had the instruction to try to integrate all this together with a single sign-on. So our team put in their effort to create a technology that allows a all-in-one app framework. So currently, this is already live and operational, available on Play Store and App Store for the NUS community. If you have an NUS staff or student or visitor account, you can actually log in and see for yourself. What happens inside this framework is that it's a single sign-on. Every single mini app within the framework, okay, will share this particular information, and it enables apps to share other key information. So we are looking forward to a future whereby we can click in terms of a location on the lesson schedule, and then straight away it can activate the navigation and at the same time show our students the bus real-time timing. So with this framework, we also thought of a lot of other applications that this technology could bring. I will share that later on. So combining all these things that we have, all the various capabilities that we have within our team of 60 people, we want to try to begin with NUS and then reach out to the rest of Singapore so that we can translate some of this valuable research and technology from paper publications and conferences into real-world applications. So we try to do some applications and try to push some of this technology to the industry. One of the items that we are working on right now is an engine that does optimization and real-time routing. So this is in collaboration with the Land Transport Authority for on-demand bus service. So with that routing, this is a video of our platform that allows such routing. So it could be used for bus, it could be used for logistics or any scenario with multi-vehicle. So what happens is that the planner could actually plan for a variety of vehicles, okay, having different capacity, needing to visit, send goods to different stores, for example. So this is actually a live platform, and we have a driver's view whereby the planner can freely select a particular store that is assigned to truck 1, for example, the second stop, and assign it to truck 2, and you will do a live update, and then the driver's view will actually get a prompt. So this is one of the things that we are trying to push out to the logistic industry, because in terms of mathematics, this multi-vehicle routing problem is a very tough nut to crack. Next. So on top of that, we also want to try to do some form of simulation. So traditionally, GIS and simulators often have a big gap. So we have a team doing simulation engines. So we are building a I would say a bridge, a connector to allow simulation events, thousands and thousands of events per second, to be able to stream over the web to a GIS type of platform, any locational platform, to be able to visualize thousands and thousands of movements and simulation within the second itself. So that's what you see on the right. This is a simulation of MRT trains and LRT trains moving with a particular setting. So we are coming up with the interface is still in prototype stage. The planner will be able to interact with various parameters, such as train to train type of headway, such as the time of how long the door should stay open for, and you can straight away see in real time how it affects the entire system as a whole. Right. Another item on the left, previous, is that we are trying to create a new map app for Singapore. So for Singapore, what happens is that there are many apps available to the consumers for navigation. There's Google Maps, there's One Map. Esri provides a navigation app as well. But what really makes it different is firstly, how the app actually routes. Secondly, the set of data. So we have invested in a lot of interns during their holiday time to actually collect data. So one of the key advantage of using this particular navigation app is that it allows you to select whether you are going to drop off a passenger because you are a taxi driver, or you need to find a parking, or if you are a truck driver, you need to go to the unloading bay. Especially in town area, right, these entrances may be different. You may need to enter at a different road, and if you miss a particular turn, right, it could mean that you need to exit the ERP area and re-enter and pay another charge again. So this is quite important. Within the app, we also collected a lot of food data, which GIS lead Shu Chen actually led the effort with a lot of student interns. So today, if you search for food from online, what you are getting are results from cafes and restaurants, but you are not getting results from hawker centers. So what we have is every single food store registered under NEA collected in the entire data set. So today, if I look for the nearest nasi lemak, it doesn't need to take me to a famous restaurant that could be quite far away. 2 blocks behind me, downstairs Kopitiam, the store can be found in our data set. Next. We have another team that's doing computer vision. So we are able to, through a video analytics, through security cameras, be able to pick up human pose, whether they are occluded by the table, be it you are sitting down, be it you are walking and you pass by somebody, all right? This human count will not go down. Any occlusion of the leg, half body, the shoulder, whether the face is facing left or right, you can see the points on the eyes are also detected. So this enabled us to do behavioral type of analysis. From a location platform point of view, what we are trying to build is this connector, this engine that translates CCTV analytics information into geospatial layers. So imagine with CCTV, straight away in the near future, we are trying to create that. You have a 2D map with points of every single human where they are. We are trying to bridge this gap together using 60 Full HD CCTVs of I4.0 building. Right? So combining a lot of this, is then possible to think of very bold ideas such as a smart retail solution, whereby today you may have a Starbucks card, you may have another card for Giordano and all these cards. So what happens is that we envision a future whereby it's an all-in-one app for retail. For all shopping centers, you just need an all-in-one app to store all your cards, all your various rewards, and this enables the retailer to actually increase their sales in terms of pushing proximity-based vouchers, limited time voucher, whereby in the afternoon a restaurant may have a lot of empty seats, all right, I can push to you a 50% discount voucher if you come in to dine within the next 30 minutes, right? It will be a time limited because it doesn't make sense if then you take the voucher and come back during the weekend, during the peak hour, right? So this is something we envision with all the indoor positioning, so on and so forth. We have many other projects, including the gate analysis, including smart food and even smart health. We use this technology to help MINDEF and DSTA create the next IPPT app. I'll leave that to the development team. Currently, we finish detection of all the sit-up, push-ups, and we are now doing the 2.4-kilometer run. So you can envision next time, no longer need to go back to army camps to take IPPT. You can do it on time, on target, right? Okay. Regarding the simulation part, in terms of the simulation engine, we are currently preparing a simulation for the TUAS Megapod. So what happens is that it used to be just video-based simulation, desktop-based simulation. We are trying to build this engine to take it to the web, right? Okay, I don't have much time. I just like to tell you about our training. So if you'd like to learn more about geospatial, Esri has their training, and we also conduct training. We see some of our participants seated in the audience here. So we have 2 more trainings coming out. If you'd like to learn more about geospatial technology, feel free to contact us, right? Last but not least, to conclude, I'd just like to say, we as NUS, we are a test bed for smart city. If you have technology, if you have things that you want to try within our campus in a living condition, we have almost 50,000 people on a day-to-day basis. Feel free to contact us. We can try to implement whatever you would like to see within the campus itself. All right? And my name is Raymond, and this is Su Chen. We work under Professor Andrew Lim. Thank you.
Thank you, Raymond, for the amazing presentation. So if any questions you want to ask Raymond, now will be the time. Please raise your hand.
Yes, we have a question from the gentleman over there.
Thank you, Raymond and Susan. I have 2 questions, basically.
Okay, sure.
First one, I mean, you have mentioned that you have produced about 400 plus buildings. Is it true? Or 200?
We have produced the entire NUS buildings, both University Town and Cambridge campus, is about 240 plus of them.
For the over 240 plus buildings, I mean, what's the format that you use to produce the models?
This is basically convertible in any format. So we try to be able to adhere to CTGML, and we've tested with, for example, one of the leading vendors in this area, Dassault Systems, already last year. So we've gotten that format, but there's pros and cons converting to CTGML. So we maintain our stand in terms of our models can be converted to any of the leading formats, including Collada, SketchUp, including multi-patch in GeoDatabases.
So in case of, you have mentioned that you converted to CTGML, so you are referring to the LD3 or LD2?
Our models currently is a mixture. The definition of CTGML is quite limiting in the sense that it defines the entire building either in 1, 2, 3, or 4. What happens is, if you ask me to give you an estimate, all our buildings are about LOD 3.5, but of course there's no such thing in definition. That is to say, at the ground level, the open space level common areas whereby it's a main thoroughfare where hundreds of students and visitors walk past on a daily basis, these are modeled to interior. For private offices, whereby it sort of have a lesser audience that will benefit from the interior, we model it to LOD 3.0. For certain areas, it could go down to 2.5, and that's the least that we have.
Okay. Then my last question.
Yes.
How much time do you spend from the data capturing to the data modeling?
From the data capture, we fly from drone flying, from terrestrial LiDAR scanning, mobile LiDAR scanning, handheld LiDAR scanning, everything all in all, let me calculate, about 1.5 years to create this very precise set to enable machine learning. About that, 1.5 years.
Okay. Thank you.
All right, thanks for your question.
Anyone
Hey,
else?
yes, sir. I have another question here.
Buildings and landmarks.
All right, the question is, what's the approximate data size? Okay, in terms of the point cloud, just based on terrestrial, total number of points more than 40 billion. In terms of photogrammetry, drone-based for the entire university town and the Cambridge area, we have 440 million and above. That's the number of points in there. So what happens is that later on this year, we will roll out a portal whereby researchers can actually freely clip and download all these pre-labeled data points to run their various algorithms to see who has the best automation to convert points into geometry.
Also, did you have to manually map out the buildings and like
Yes.
all the landmarks? Like,
In order to do this first set of ground truth, the human expert must teach the computer what's the best an expert can model, and that model must match the points as accurately as possible for this algorithm to be able to do a deep learning type of model accurately. If the geometry is generalized, it doesn't matches the points, then it's very confusing for the machine to do any statistical learning.
also, I'm curious about like the total data size in like terabytes or like petabytes.
Okay, how about let me anticipate what you're asking for. Over here, the entire virtual NUS is streamable onto a mobile phone. So on my mobile phone, loading is within a second for an entire LOD 3.5 full set of building. Any building, click on it, it will load instantaneously. That's the optimization part of things. Yeah, so in terms of actual data size, I hope if this is your concern, we have already breached that gap. So it's usable on a mobile phone. Within the web itself, do not need an app. Okay, any other questions that we can help to answer?
I'm afraid that's all the time we have for now.
All right.
But do feel free to catch up to Raymond.
Yeah. If you'd like to
individually
see
right
see
after.
a live demo, feel free to look for us. Right, we have a very limited time over here for the event.
Just to conclude, we all have been hearing about digital twin as a buzzword for years, and it's great to see one real application on such a broad spectrum from the NUS. And not only is the NUS inspiring Singapore, it's also inspiring schools across the world. So we've been going to school 10, 20 years before, and we look at how we can do as a school now. Let's just anticipate what we can do with GIS 10, 20 years later.
Yeah.
So on that note, thank you guys so much
All right, thank you.
for your undivided attention. And we'll see you back in 5 minutes where we'll be talking about ArcGIS Pro. Thank you.